This is an interactive visualization for Euclid's elements. Euclid was an ancient Greek geometer around 300 BC, known as the father of geometry. He is famous for his treatise, Elements. Euclid's Elements consists of 13 books filled with 465 geometric constructions called propositions. Many of these propositions can be constructed with just a straight edge and a collapsible compass. Despite its simple toolset, Euclid's Elements involve some very complex constructions. What sets Elements so far apart from other ancient mathematical works is that Elements was axiomatic. That is, it systematically compiled collective mathematical knowledge from a set of mathematical building blocks called definitions, postulates, and axioms. Definitions simply define geometric terms, such as, a line is breadthless length. Postulates are geometric assumptions, such as, a straight line can be drawn from one point to another. Axioms are sometimes called common notions. They are basic logical statements that are assumed to be universally true, such as, things that are both equal to the same thing are also equal to each other. Elements takes these building blocks to build propositions, and uses previous propositions to build bigger, new ones. Today, comprehensive collection of mathematical knowledge is essential. We need to know what our mathematical theorems are built on top of, or else how would we know that they were true? To me, Euclid's Elements represents a major milestone in human history, where we started asking not just what we know, but how we know it. When users open the visualization, they see this book, which gives an introduction to the program on the left page, and a brief history of Euclid's Elements on the right. Pressing the right arrow key, or clicking the right arrow button, takes the user to the next two pages, which give a brief tutorial on how to use the Straightedge tool and the compass tool. The user can then either start solving propositions, or use freeform mode, where they have full freedom to create straightedge and compass constructions. Proposition 1 is to construct an equilateral triangle on a given line. Users can follow the steps on how to work through each proposition. They can hide steps if they wish to work through the proposition on their own. To draw a circle, the user can press C or click on the compass icon. They can then click on the origin point for a circle, and then click on another point they wish for the circle to pass through. When lines or circles intersect each other, they create intersection points that new shapes can use. To start drawing lines, the user can press R or click the ruler icon. To construct an equilateral triangle and complete proposition 1, draw a line from this intersection point to the line's endpoints. Proposition 2 is significantly more complex than Proposition 1. The goal is to draw a line which is equal in length to a given line and has a given point as an endpoint. Start by drawing a line from A to B. This proposition uses the previous proposition as a building block. Click on the bolded text, Proposition 1, or click these shapes and select Proposition 1. Postulate 2 says that a finite line can be extended into continuity. While using the ruler tool, extend a line by clicking the endpoint it should be extended from, then clicking Extend. Do this for DB and DA. Draw a circle with origin B that passes through C. This creates intersection point E. Draw a circle with origin D that passes through E. This completes the proposition. It can be difficult to immediately see why a proposition succeeded. Click See Explanation to see why. This adds an explanation of why the proposition passed. Click on the book, and click Proposition 3 to go to the next proposition. This one is much simpler than Proposition 2. First, use Proposition 2 to create a line with a given length on a point. Click the line CD to get the length, and click point A to get the point. Now, simply draw a circle with origin A, which passes through E. So far, I only have the first 3 propositions of Book 1 from Euclid's Elements implemented. I built this program for scalability, so more could certainly be added. Any straightedge and compass proposition from elements can be performed by the program as it stands. However, some would require the construction of many shapes, because so many propositions rely on previous ones, which rely on propositions that came before them, and so on. For instance, Book 6 Proposition 30 is to cut a line in extreme and mean ratio, or as we would call it, the golden ratio. I really wanted to implement this one. Unfortunately, this relies on many prior propositions. It directly uses two propositions, the first of which, Book 6 Proposition 29, relies on 6 more propositions. The first of those, Book 6 Proposition 25, relies on 7 propositions. This chaining of propositions continues, growing exponentially complex. I think that it really speaks to Euclid's ingenuity that he was putting all these propositions together like this. He probably didn't draw out the hundreds of shapes required to make the golden ratio. Although the steps Euclid gave to complete Proposition 3 are simple on paper, they include a much more complex set of steps to work out using a compass and straightedge. It is clear that Euclid prioritized encapsulation of prior work to create building blocks to add to his toolset. This reminds me a lot of functions in programming. Programmers use functions, which are essentially an encapsulated set of steps. For instance, a function called drawFace may draw a circle for the head, draw a circle for the left eye, draw a circle for the right eye, and draw a line for the mouth. Every time a function is called, the computer runs each of those steps, but it is easier for the programmer because the programmer only needs to say, draw face. In Elements, Euclid only says do proposition 2, while actually doing this with straightedge and compass construction takes a complex series of steps, and this encapsulation becomes exponentially more complex with later propositions. I think this points towards how abstract and ahead of his time Euclid's reasoning was. There still are other propositions that can be done without much excess. For instance, Book 1, Proposition 22 is to construct a triangle out of 3 given lines. We first construct a line that is longer than all 3 lines combined, and use Proposition 3 to create a line the length of the longest line. On the remainder of the line, use Proposition 3 again to create a line the length of the medium line. And on the remainder again, use Proposition 3 to create a line the length of the shortest line. Then on this line, create a circle with the radius of the longest line, and another circle with the length of the shortest line. Connect these intersection points, and a triangle with 3 given side lengths is constructed. Another one I like is Book 4, Proposition 15, to inscribe a hexagon in a given circle. This could be done after Proposition 1 by adding equilateral triangles to an arbitrary radius. However, Euclid didn't do this for another 75 propositions after he initially could have. He uses Book 3, Proposition 29 to help prove the correctness of his construction, so that is likely part of the reason he delayed the proposition so much later than necessary. This project was a lot of fun and presented some unique coding challenges I had never faced before. For the first couple days working on it, I kept telling myself that if I did not get a couple tricky factors to work out, I would need to scrap the project. Otherwise, I could see myself spending way more time on this than I wanted to. Fortunately, I worked out my major concerns, and I'm really happy with the result. I learned a lot I didn't previously know about elements while doing my research, and I learned a lot more while working intimately with the constructions of some of his propositions.